Very good morning, dear friends. So today we will move on to this is the third video in the series of radiation measurement. Okay. So in the last two videos, we have seen in the first video we have seen about what is the basics of radioactivity. The last video we have seen about gas-filled detectors, particularly the proportional counter, ionization chamber detector, as well as the GM counter. Okay. In continuation of the same, here we move on to the solid state detectors. Okay. So first we are going to see about uh, scintillation detector. In this video we are going to see two main types of detectors. One is a scintillation detector, second one is called as semiconductor detector. So we'll see these two in details. Okay. How we'll see the principle, operation and working of these two types of detectors. So first we'll take up scintillation detector. See the name scintillation. I'll just write it scintillation. Okay. Scintillation is done by means of a scintillator. Scintillation is a mechanism which is done by means of a scintillator. Okay. So what I mean by scintillate? So scintillate or scintillation is a mechanism to, the meaning of this particular term is called as to glow. It's a very common term. Okay. If a person is very bright, okay, so you can call him as is scintillating. Okay. Is very face is very glowing. Okay, something you call it as scintillate means to glow. Okay, so that itself will give you a clue, something it is connected with light. Okay, whenever we have the word scintillate, it means to glow. Okay, something it is connected with to light. So what is our requirement as far as radiation measurement is concerned? We'll be having a photon of radiation. Okay, you will have a photon of radiation. This radiation has to be absorbed by some mechanism, some medium or some mechanism by which this radiation of photon should be absorbed. Because of that absorption, it should convert into an electronic current or a electronic pulse. This can be measured. This is our main aim of our radiation detector. If you remember, we told that two factors in these types of detectors. First factor is the energy. The energy should be equivalent to, proportional to the height of the output pulse. Height of the output pulse. Okay, this is the first requirement we have given. Second requirement is how many number of radionuclides are there, number of atoms that are present. Okay, should proportional to the number of pulses. Okay, number of pulses. So this there should be a strict proportionality between two. This is the basic condition of the radiation detector. This is what we have seen in the previous video. If you have doubt, you can see the previous video. I will give the link of the previous video in the description also. Fine. So this is what is the main condition for a radiation detector. Okay. Now we will move on to our scintillation detector. If you say this scintillation detector, it is actually consisting of two parts. The scintillation detector actually consists of two parts. So the first part is called as scintillator, and the second part is called as PMT. PMT is very popularly called as photo multiplier tube. Okay, so this is a photo multiplier tube. Very simple. So these two put together, you call it as a scintillation detector. We'll see the construction. So basically it consists of a scintillator, a material which is going to do the scintillation. Okay, then we'll have a photocathode. So this is your scintillator, this is your scintillator, this is your photocathode. Okay, so after photocathode you have what is called as PMT. This is called as PMT. what essentially you have in a PMT. In PMT, you have a set of electrodes. You have a set of electrodes. So these set of electrodes are called as diodes. These set of electrodes are called as diodes. Okay, what is the specialty of these set of electrodes? It will be increasing voltage. Say if this is 100 volts, so this will be at 200 volts, this will be at 300 volts, this will be at 400 volts, and say this will be at plus 500 volts. Okay, so it will be in the order of increasing. Okay, finally you will have some sort of electronics circuit which will convert this into an electronic pulse and you can measure it. Okay, so we'll see what is the underlying mechanism of this scintillating detector. As I told, it has two parts. One is the scintillator. The second part, the entire part, this entire thing is called as PMT. Okay, so what this scintillator does, that is the first question. Okay, so first we'll assume incoming radiation. So it can be a alpha or a beta particle that interacts with your scintillator. As I told you, the scintillator is normally it can be as simple as it can be made up of phosphorus, okay, or it can be made up of the most common material that is used for scintillator is cesium iodide or sodium iodide, okay, or these are the most common elements that are mostly used for okay, mostly used for our particular element of scintillator. So what happens actually inside this scintillator when the incoming radiation comes? Okay, you know that these type of radiation will be very high. Okay, normally whenever we talk of radioactive substance, the energy of this radiation is very high. Okay, so when it interacts with this scintillator, okay, what essentially does is that the molecules of this scintillator, when they absorb this high energy, they get abundant energy. Okay, because of this abundant energy, so we know that valence band, conduction band, no? Okay, so all the atoms, molecules, when they given extra energy, they move from the valence band to the conduction band, or a ground state to the excited state. Okay, they move, and we know that they cannot remain in longer state in excited. They come back to the ground state. When they come back to the ground state, they emit the extra energy. Here the emission is in the form of a light. Very interesting, right? See, when the radiation attacks, whenever the radiation falls or interacts with your medium scintillator, okay, what basically, if you put it in simple words, it absorbs the energy radiation, and converts that into light. That's the simplest explanation. It converts that into light. But how it does that? Basically, when it absorbs the radiation, the molecules inside this substance will absorb that radiation and will move to the conduction band, excited state. When it comes back to the normal, it emits that output in that extra energy it has gained in the form of a light. Okay, that is the interesting part. The emission is in the form of light. That is the important factor. Okay, so that light, the light that is emitted, okay, so the amount photon of light that is emitted is proportional to the photon of light is proportional to the incoming energy of your gamma particle or your whatever the type of particle. Okay, proportional to that energy, this will be light photons will be produced. That is the first stage of your scintillator. Okay, so each element will have different kinds. For example, sodium iodide for gamma interaction, cesium iodide for beta interaction. Okay, so you have different elements for different kinds of interactions. Fine. So the next part is our photocathode. Okay, photocathode, what fundamentally happens in your photocathode? You remember, photocathode actually facilitates photoelectric effect. It facilitates photoelectric effect. What is photoelectric effect? Whenever light falls on a substance, whenever light falls on a particular substance, this absorbs the light, and when the light is above a certain threshold, when the light photon energy, the light photon energy the light photon energy is above a threshold, it will emit electrons. It will emit electrons. This is the principle of your photoelectric effect. The same principle appears here also. So from the scintillator, you will have light photons. Okay, this actually falls on your photocathode. This actually falls on your photocathode. This photocathode, proportional to these light photons, it will emit electrons. It will emit electrons. That is the purpose of your photocathode. It is a simple light detector. Okay, so proportional to the light that is falling on this photocathode, it is going to emit electrons. Now this emitted electrons will travel into our photo multiplier tube. Okay, so this is the last part of our detector. The first part is the scintillator, second part are the photocathode is also part of the photo multiplier tube. Okay, so we have entered into the second region. From the first region, the radiation is entered into the second region in the form of electrons. Now the radiation is taking the form of electrons. Okay, now what happens? So now we are this is the starting stage of your photomultiplier tube. This is the photocathode, where you have a good number of electrons which are entering. Okay, say these are the primary electrons. We can just put them as the name as primary electrons. Okay, when these primary electrons enter your photo multiplier tube, inside the photo multiplier tube you have a set of diodes. The set of diodes is such that it is operating at different potential, and another important structure is that the potential is increasing. The potential is increasing. Okay, now what we are trying to do is that we'll try to focus all these electrons. We'll focus all these electrons, okay, onto the first thing, which is having a potential of 100 volts. What this particular thing it will do, again it will actually, this particular of this arrangement is, it's an electronic amplification. It is an electronic amplification. Okay, we are trying to amplify the signal into multiple fold. We are trying to amplify the signal multiple fold. Okay, for each primary photoelectron that strikes your first diode, it is going to produce two secondary electrons. See, it is going to produce two secondary electrons. So for each primary electron that strikes your first diode, it is going to produce two secondary electrons. Okay, so this is operating at 200 volts, say. Okay, so this process is going to continue. So for again, see, for the first primary it produced two secondary, again each secondary is going to produce another two secondaries. Okay, and so this process will actually if you actually go further, it will be multiple electrons are getting created. Okay, so we are, by using potential at the increasing order, we are actually amplifying the electron rate. Okay, multiple photoelectrons are being produced. Okay, so thereby when it reaches your output stage, the output is very much amplified. It is an amplified signal. Okay, so this particular signal is then measured with a suitable simple circuitry, where it can show you how many pulses are reaching the detector. That's it. Okay, now you can see where we started. First we had the scintillator, which converted the photon of radiation into light, Second, this light made to fall on your photocathode, which emitted electrons, primary electrons. These primary electrons are accelerated by a special arrangement of the photomultiplier tube. Okay, so which amplifies your signal, thereby you'll be getting a very good signal. Okay, so this signal is an electrical signal. Okay, so this signal is proportional to the amount of primary electrons that are produced. The primary electrons are in turn proportional to the amount of light that is generated by the scintillator. The light in turn is proportional to the energy of the incoming radiation. Okay, so this is how your scintillating detector works. Okay, that's the basic principle of your or the working of your scintillation detector. Fine. Okay, so this is the first kind of detector we have seen under solid state. So we'll move on to the second kind of detector, which is nothing but semiconductor detector. Okay, so semiconductor detector is a far more which is used nowadays also. Okay, so these type of detectors have better output in the terms of what I mentioned by better output is it has a very high energy resolution. A good sensitivity. Okay, what I mean by energy resolution is it is able to differentiate with very low incoming radiation with a very high radiation, even when two energy radiations, okay, when two energy is in close vicinity. Okay, so this is one particular radiation and this is another radiation. It will be able to differentiate between these two radiation. Okay, that is the advantage of semiconductor detector. Okay, so we'll see what this semiconductor detector is that and how it is working. Okay, basically we know some basic physics, electronics. What is a semiconductor? So we have different elements. One is a conductor, one is an insulator, and third one is an semiconductor. This is somewhat very basic physics. Okay, so from basic physics we'll jump into the actual mechanism that is going to take place. So we know that in a normal insulator you take, so there are two bands. One is the valence band, second one is the conduction band. So all these concepts arise basically if you take any atom or a molecule. Okay, there will be two kinds of electrons. One is free moving electrons, second one is tightly bound electrons. Okay, either it can be freely moving electrons or bound electrons. When we have more amount of freely moving electrons, okay, this will contribute to the conduction. When it is tightly bound electrons, it will not contribute to the conduction. Okay, so what I mean by free moving electron is there is more electrons in the conduction band. What I mean by free moving electrons is there is more electrons in the conduction band. If there are more electrons in the valence band, okay, the valence band is bound, okay, then there will not be any conduction at all. If more electrons are there in the conduction band, free electrons are available in the conduction band, then that particular will have some conduction. That's a basic thing. Now we'll see what is a conductor, insulator. Okay, so if you take an insulator, for an insulator, again we'll just illustrate these two bands. First one is a conduction band. Okay, I'll just draw the conduction band here also. I'll use another color. This is for an insulator. This is an valence band. Okay, this is an sorry this is an valence band. This is for a conductor. See, in insulator and a conductor you can see the difference. This is your conduction band, this is your valence band. Now in a insulator, the difference between the conduction and valence band, which you call it as the energy gap, is very high, is very high. So an electron, for it to jump from valence band to conduction band, it requires very high energy, or practically it is not at all possible, because there is a very big band gap. Because of this band gap, they don't conduct. Okay, no conduction means it is called as an insulator. Whereas a conductor, you can see the limits. The valence band and the conduction band limits are zero, or it can be also be overlapping. In that cases, you can have easy conduction. Whenever electron jumps from valence band to conduction band, it creates a hole. Okay, it creates a hole, a vacancy site, positive ion. Okay, so this type of conduction, this type of moving of free electrons will facilitate conduction. This is a conduction. It has absolutely zero band gap, or it has overlapping even. Okay, now we'll take the case of an insulator, I mean our semiconductor. Our semiconductor, as the name indicates, it is something in between your conductor and insulator. The name given, semi. Okay, semi solid, the name is semi. Okay, what it means by semi is it will have a valence band and it will have a conduction band. Okay, this is your valence band, this is your conduction band, but the energy difference is very minimal. It is something in between your insulator and your conductor. So by thermionic emission or some kind of excitation, some of the electrons from the valence band, they can absorb the energy by the excitation and they can move to the conduction band. When they move to the conduction band, they will contribute for conduction, they will contribute for electricity conduction. So whenever they move, they create a hole. So this is called as an hole, that's a positive ion, this is a negative ion. Okay, so presence of a positive ion and a negative ion will be contributing towards electricity. This is a basic physics, I'm not going further. This is in a semiconductor. This is how your semiconductor works, you already know that. Okay, what we are trying to accomplish here is, okay, we are using two semiconductors. We are using two semiconductor, one n-type semiconductor and one p-type semiconductor. As in this figure, we are using a n-type semiconductor. Okay, and we have a p-type semiconductor. Okay, we have a n-type and a p-type semiconductor. Okay, now the interesting part appears. So these two are, this is a p-type. Okay, p-type means, so basically the semiconductors are doped with some impurities, thereby in an n-type semiconductor, the dominant ones are electrons, dominant charge carriers are electrons, and a p-type semiconductor, the dominant charge carriers are holes. Okay, here you have electrons, you have here the dominant charge carriers are holes. Okay, this is a p-type and an m-type semiconductor. When they are both joined together, this particular thing is called as a p-n junction diode. We call it as p-n junction diode. Okay, so very interesting mechanism takes place. So when you provide the appropriate potential, when you provide the basically when the p-n junction are joined together, what happens? In the n-type you have the dominant electrons, here you have the dominant holes. These n-type electrons will try to diffuse inside this particular region, these holes will diffuse inside this region, and you will get a very fine region of ion recombination. This particular region is called as depletion zone. The forbidden zone or depletion zone. Okay, depletion region. You can put it as depletion region. Okay, you'll have a depletion region that is getting created. Okay, so whenever you apply a potential like n type, you apply a positive, and a p type you apply negative. Okay, suppose you applied a forward bias, p type you connect it to positive, n type you connect it to negative. What happens? Like poles ripple, so the depletion region further decreases. So the natural tendency, since this is negative and this is positive, the natural tendency for the electron movement will be in this direction. The natural tendency for the hole movement will be in this direction. Okay, this is called as forward bias. So the diode will be conducting, the depletion region will very much decrease. Suppose on the reverse, if you connect, I'll just remove this also. On the reverse, if you connect a positive, here you have positive, right? So so reverse bias, if you connect a reverse bias, what will happen? If you connect a reverse bias, the reverse operation takes place. Okay, they try to move away. Okay, thereby, so the reverse operation will be, the n is connected to positive, this is connected to negative. What happens? It will be attracting this, the normal direction will be in this way. It will be moving away. Thereby, the depletion region will be increasing. Okay, because of this increasing depletion region, there will be no current or very less current. Okay, this particular arrangement is called as reversed bias potential, reversed bias condition. Okay, so we'll see now, we'll apply a potential. This is a reversed bias operation. Okay, we are applying a reverse bias. In our reverse bias, the depletion region will be very large. Okay, now for our this particular junction diode to act as a detector, we require a very big depletion region. This is the one that is going to contribute, towards our radiation measurement. We'll see how. Okay, and also in the same circuit, I am using a load resistor where I am going to measure the output. I'll just put RL. This is the potential, we are going to measure it. Now what we did, we have put the PN junction reverse biased. Okay, because of this reverse bias, we will have a very big depletion region. Now, because of the big depletion region, literally there will be zero or no current. Okay, now the interesting thing happens. I will make the radiation to interact. I'll make the radiation to fall on the semiconductor. We know that this particular semiconductor has a very, very high energy. Very, very high energy. Typically, I'll just put the energy in terms of 4 to 10 mega electron volt or million electron volt. We can put it as million electron volt. Okay, but for an electron to jump from conduction from one this to another part, the typical energy that is required is say around 3 electron volt. The energy that is required for conduction to take place, okay, is typically 3 electron volts, but the incoming radiation is say 1000 times larger signal. So what it will do practically, because of this high energy, what essentially it does is that it will create, it will collide with the molecule, okay, thereby that particular molecule or the thing will be converted, because of the high energy, it will be converted into electron hole pair. It will be converted into an electron hole pair. Okay, I'll just put H. Because of the very high energy, okay, because of this very high energy, so the electrons jump from valence band to the conduction band. Okay, so because of this very high energy, the electrons jump from the valence band to the conduction band, creating holes. Here will be holes, here it will create electrons. So whenever the radiation interacts with your semiconductor substance, because of the very high energy, a good number of electron hole pairs are generated. A good amount of electron hole pairs are generated. These electron hole pairs that are generated will constitute a current. This current will drop across your resistor, which you measure what is the potential. This is the very basic idea of your radiation detector. What you do, you may put the radiation detector in reverse bias. Thereby it is in depletion region is very large and very less current or zero current is available. Okay, now what you do is that now you expose it to a radiation. When the radiation falls on it, when it absorbs the radiation, more amount of, because the energy is very much high, it will, when the energy is very high, very less energy is required for the electron to jump from valence band to conduction band, but it is 1000 times large energy, so it will facilitate more amount of electrons to jump from valence band to conduction band, thereby creating abundant electron hole pairs. It will create abundant electron hole pairs. These abundant electron hole pairs will contribute or constitute a current in the external circuit. That current you are just measuring it, that will be proportional. The current that is flowing in the external circuit will be proportional to the number of electron hole pairs created. These electron hole pair creators are in turn depending upon the energy of the incoming radiation. Okay, so this particular circuit, even when you have a very less energy, okay, incoming radiation, even if it has a very less energy, it will produce good amount of electron hole pairs. It will produce a good amount of electron hole pair, abundant electron hole pairs, which in turn will contribute to the current, okay, and which is measured as a drop as a potential. Okay, so that's what the mechanism basically happens in your semiconductor detector. Because of this nature, because of this particular thing, it will be able to discriminate, different radiation of different energy. It will be able to discriminate energy of different radiation. That's why the energy resolution is very high. The energy resolution of your semiconductor detector is very high. It will be able to differentiate even very closely available radiation. Okay, so that's it. And further, because already I told you, in reverse bias condition there will be very less current. To reduce literally the current to zero, the entire semiconductor diode, it is kept in a cryogenic cool environment. Okay, extremely cold environment. Okay, it is maintained with some liquid nitrogen. The entire thing is cooled. Okay, because of this cooling, okay, this cooling actually at this particular low temperature, literally there will not be any conduction possible. That is the basic idea. What we want is, when there is no conduction, when there is no radiation, there should not be any current in your diode. we don't want current in the diode. Okay, we don't want, that is current, there will be some minimum reverse current, but we don't want any current. To reduce that thing, you are placing it in a liquid nitrogen. The entire arrangement will be in a liquid nitrogen, so that it does not conduct under normal state. Under normal state, there will be zero output. Only if there is an incoming radiation, because of this high energy, the molecules will move from valence band to conduction band, thereby creating lot of abundant of electron hole pairs. Okay, this abundance will create an current which will be measured. Okay, that's how your semiconductor detector works. So we have seen two kinds of detectors. One is scintillation detector, which has a scintillator and a PMT. Okay, the second kind of detector we have seen is a semiconductor detector, which is your normal PN junction diode in reverse bias condition and kept in a cool environment. Thereby it will conduct only when a radiation falls on it. Okay, so the radiation alone will contribute to the outcome. Okay, so thereby you'll be able to use it as a radiation detector. So these two are very good solid state detectors. Okay, so in the next video we'll see about gamma ray spectrometer. Okay, so again, if you take any gamma ray spectrometer, it essentially contains either a scintillator or semiconductor detector with some associated electronics, either as a scintillator or a semiconductor detector. It's a basic thing again. Along with it, it has uh, some more associated electronics. We also have we will be studying about what are the interactions of gamma ray with material. Oh, that will be also very useful. Okay, so thank you friends.